Hi, here to talk about Chapter 10, Section 9, solving sine of theta equals k. Able to go a little bit easier in this section because usually when I teach Section 5, the second part of the unit circle, I go a little more in depth than what the book requires. I want to kind of go back to earlier stuff in this chapter and back in geometry days. So first thing I want to say, when we talked about the law of cosines earlier in this chapter, we said that going back to the triangle congruence theorems, that worked when we knew all three sides of a triangle. So if you know all three sides, we could find any angle with law of cosines. And that also worked with the side angle side triangles. If we knew the green side here, this angle here, and this red side, we'd be able to find the other side of the triangle. Then when we went on and said for law of sines, for that we said that worked for the angle side angles. If you know two angles of the triangle and the side in between, you could use law of sines. Or if you had the angle side. So two angles and then the next side. Now, law of sines also works for the side-side angle triangle. The problem is it's not a congruence theorem, going back to geometry days. And kind of want to show why. So I have two triangles here, and I don't know if this is worth drawing, probably not worth drawing out the triangles. But with this, we'll notice the two are the same. I'm going to take this bottom one here, and so they're both these side-side angles. I know a side, and I know the angle that's not between them. Well, if I take this red one here, and I'm just going to flip it left and right, so I didn't change the length of it any. If I drag that over here, still haven't changed the length any. Now, so it's still going to be 9 long. But now if we look at what happens though, if I'm trying to find this angle here using law of sines, I can do that, but the problem is, which angle does my calculator give me? That I have two totally different looking triangles that both fit this side-side angle, or angle side-side. Some people remember it that way. So your calculator really has to decide, does it give you this larger, this obtuse angle, or the smaller one, this acute angle? And it by default is going to give you this angle here. So if we were to go through and do this problem, I'll scroll down a little bit further. I'm going to go through and let's label up our triangle and say, why not, we'll say this is side A, side B, and side C. Then by default my theta has to be capital A, angle A, so we're just labeling it like we normally do for law of sines or law of cosines problems. Well, now if we're trying to find A, we could do that because we have a pair, we know both B's, so we could say sine of B over B equals sine of A over A. And then I'm going to just kind of work to the side this way because I'm running out of space. So sine of 20 degrees over lowercase b's, that's 9, equals sine of theta, that's my capital A, was my theta, over lowercase a, so 15. Some people go through at this point and they cross multiply and divide. It saves you a step if you just multiply by 15. So you get sine of theta equals 15 times sine of 20, all divided by 9. So sine of theta, I'm going to punch that in a second. So if I grab my graphing calculator and say whoa, that's not where I meant to be. Let's clear out of there. And just, oh, I'm hurting today. Alright, so make sure we're in degree mode. Go here. Alright, so 15 times the sine of 20 degrees. Make sure I add my parentheses, divided by 9. So I get sine of theta equals 0.57000, so on. So if I do inverse sine of my answer, then I include all those decimal points. I come up with the acute angle, the smaller angle being 34.75. So 34.75. So then at this point, if I were to do inverse sine of both sides, 34.75 degrees, I think it was. And I think this was 0.570, some other stuff. I'm like going back and show my work later. So I had sine of theta equaled something like this. I did inverse sine to cancel that out. and give me theta. So if I do inverse sine there, including using my answer button, so I don't have rounding within the problem, I get 34.75 degrees. And now then, let's say that would work for this triangle. But what in the world is it going to be here for this other one, where we have this angle that's larger than 90 degrees? And that's going to be this next one. So if I were to say, on my unit circle, it just gave me that the angle's 34.75. So right about there, something like that. And well, now our calculator then just has to decide, what does it do when it sees sine of theta? So this is, not sure exactly what you're going to write for your notes for this, but it saw sine of theta equaled, let me jump back a slide, 0.75 if I remember right. Nope, sine of theta was 0.57. And so if I have 0.1, 2, 3, 4, 5, 7, so that makes sense. Right about there is my 0.57 degrees. So it sees that the y value there, because we're talking about the sine of theta, we know that the y value is on the unit circle, is the sine. And we know it's 34.75 degrees. Well, it just knows this height is 0.57. So when it does the inverse sine, it chooses to give me the smaller angle. But it really has two options, that if I go back here to my dashed line and pop a horizontal in there, there's two spots on the unit circle that have that same exact height. So it needs to decide which one it gives me. The other one is going to be this spot here on the unit circle. And that then, my other angle could be this larger angle, this green angle. And that would have been my top triangle on the last slide. Well, how do you get that? Well, if you look at the symmetry in there, we know that this angle here could also be 34.75 degrees. So going back to what I kind of already did in section 5, if you're just trying to find this green angle, you could say, well, that's going to be, if I would do this whole 180 degrees, gets me over to my black x-axis here, the negative x-axis. If I subtract the 34.75 degrees, so 180 degrees minus 34.75 degrees, then that angle is going to end up being 145.25, if I did my math right. So in other words, we should be able to take and do 34.75 degrees. If we do the sine of that, we should get a certain height, 0.57. That should be the exact same as if I were to do sine of 145.25. And if we were to try that, so sine, and I did a little bit of rounding here with my 0.75 there, but we're going to be real close. If I do sine of 145.25, again, I did a little bit of rounding, but essentially I have that same 0.5700, you know. Once you round up here, you're going to be getting your zeros. So that's what you have to do then when you get triangles like this, to figure out, well, what's the other angle that has that same sine value. You just need to know that, well, sine values are looking at the height, so then you find what two spots on the unit circle have that height. Then you can go through and use your angles to find what's the other one going to be. You could do the same thing with cosine. Let's say we're working through a problem and we come up with partway through something like cosine of theta equals 0.3. Well, if you wanted to figure out what theta is, you could go and do the inverse cosine to both sides, and you could come up with your angle. Well, in order for that to happen, we'd be talking about, well, what two spots on my unit circle. One angle could be something like this, and here in blue then I have my first angle, and maybe I should do that. So if I do inverse cosine of 0.3, so inverse cosine 0.3, I come up with that should be 72.5 degrees, and so 72.5 degrees. And that right there, 72.5 degrees. Well, my other spot on the unit circle that's going to have, now that we're talking cosine, think of our unit circle, the cosine was always the x values. So if I pop in a vertical line here, it gets me to my other spot that also has an x value or a cosine value of 0.3. And so if I were to put in my other angle, now that angle is going to be all the way around. I wanted to switch to my green one. So that second angle then is going to be this here, this new theta. And well, how would we figure that out? Well, symmetry again. This angle is 72.5 degrees. And we know that this angle here is going to be 72.5 degrees. So if I just want this green part, I could say, well, all the way around is 360. My theta here then is going to be 360 degrees minus the 72.5 degrees. So that's going to give me 287.5 if I did the math right. So 287.5 degrees. And I should be able to go back and punch that in and make sure it works. So if I say cosine, and again I did some rounding, it really was 0.54 here, but should be close enough to show us that we actually did it right. And I come up with 0.3007 as opposed to the 0.3 that I started with. Kind of my disclaimers there at the bottom of the screen. Because the second angle for cosine is greater than 180, because now we're working vertically, this really only comes up when doing laws of sines, not really law of cosines. But at the same time, if you're trying to figure out another angle that has the same cosine value, this would be how you do it. That's all I have from this section.